The obvious question, does the Fourier transform of a probability measure, does it fully determine the measure, or do we need some conditions when this is true? The answer was studied by Paul Lévy, a French mathematician who worked in Paris about 100 years ago. I recall a story about Paul Lévy that he worked on complex analysis, and then he got a position in École Polytechnique, which is the engineering school of Paris. And then when he went there, because he got the professor position, and then he was told that, okay, now you should teach probability to the engineers. And then he thought, probability, that's kind of an ugly field of applied math. I want to do real math and real complex analysis. But then it so happened that he started to work seriously in probability theory, and he developed the theory of the Fourier transform in very elegant and very powerful way. So what we are learning now are kind of the fruits of Lévy's best theorems, probably in general probability. And the famous Lévy's inversion theorem, what does it say? It says that if you take this type of, it's a bit of a strange integral, but that's how you invert Fourier transforms on the real line. If you fix a and b and you take this type of function, and then you take the Fourier transform of the probability measure, you integrate now the frequencies from minus t to t, and then you normalize by 1 over. Now I need to check, maybe I have a mistake in my lecture now, or my handwritten notes. So just a moment. That is where, how should we normalize with Lévy's formula? No, it is, yes. I believe it's 2 pi that we need to normalize here. Okay, maybe we should check that this 2 pi is the correct normalizing, but we look at kind of longer and longer frequency band. We look at band of frequencies up to t, and now we let t to approach infinity, and we ask, okay, what should happen from this integral? It's a strange integral. We integrate with the Lebesgue measure, and because it's always a Lebesgue measure, we don't denote it by, we just write d theta. What is the answer of this a bit strange looking integral? This integral limit equals the measure mu at AB interval plus 1/2 the measure of the mu at these points A and plus the measure mu at point B. That's true for all A less than B. We are not going to prove the theorem here. What we are going to do, we are going to see what the theorem tells us in practice. So assume now that somebody gives us the Fourier transform here, and so we know what this is, and we can calculate. When we know what this is, we can calculate in principle all these integrals for all A and B. And so that means that we know the measure values of open intervals plus 1/2 the endpoints. Is this sufficient to reveal what the measure mu is completely? The answer is yes. The Fourier transform fully determines mu, and that's the wonderful result of the Fourier transform. So it completely, you don't need to assume anything about your probability measure. Just assume nothing. You can always calculate the Fourier transform, and it completely determines the measure. Let's try to understand how this corollary follows from the theorem, from this formula. Is it obvious? For me, it's not super obvious. Actually, for me, I think one lemma would be helpful first. One lemma would be helpful first. So namely this. Let's denote A for atom. So let's denote by A the set of atoms of measure mu. So this is the atom set of probability measure mu. So those points where there's a strictly positive mass. And the lemma says that this is a countable set. Is it obvious that this is countable? Give me green light if you know already that the A is a countable set, or if you are kind of obvious, of course it should be countable. Who thinks that it should be, of course, countable? Not many. Then we will use 3 minutes to check why is it countable. So let's write A as the union of. Let's see. I think I prepared one note about this. So let's write A as the union of these types of sets, those real numbers such that the mass of mu is, let's say, it's bigger than 1 over n plus 1 and less than 1 over n or equal. And what do we, let's give this a name. So let's call this one an. And then actually I claim that an is finite. So actually I claim that the number of elements in an is not big. It is at most n plus 1. Proof for this is that let's make a counter assumption. If this would be bigger than n plus 2, then there exists a set B in this an such that B contains n plus 2 elements. Then what? Then the measure of B is a finite set, so we can calculate the measure by summing these members in B by mu of the singleton set. That's how we calculate measures of finite sets. We sum of the masses. Because every B belongs to an, so each mass is bigger than, by definition, each mass is at least bigger than n plus 1. So this is bigger than number of elements in B times n plus 1. And now, wait, 1 over n plus 1. And B, we assume that B is equal to, has size n plus 2, so then this is strictly bigger than 1. But of course, this is not possible because mu B is less than the mu of the full real line, and mu was a probability measure. So then this is the full measure is 1. This is a contradiction that we found a set with bigger the measure than 1. It's not possible. So this is why the proof is correct, that the set an contains at most n plus 1 points. Is this clear? Let's clean it up. So we have verified that each set an, each of these is a finite set. Now we have a countable union of finite sets. This is a countable set. That's the end of the proof. Are there questions here? That was the lemma. Okay. Now we know that every probability measure, maybe it has a density, maybe it doesn't have a density, maybe it's discrete or whatever. Anyway, it can only have at most countably infinitely many atoms. So points with mass strictly positive. Let's prove now this corollary. Assume we have two probability measures which equal Fourier transforms. So then we actually know that by this Lévy's theorem, we know that these things are equal for all A and B, less than B. So then we know that mu1 AB open interval is equal to mu2 of the open interval for all A less than B such that A and B are not atoms of mu1 or mu2. Okay, so if A and B are not atoms, so then these things vanish. We get zeros here, and then we only look at this. And that's why from the Lévy's inversion formula, this theorem, we conclude that mu1 and mu2 are equal on this type of intervals, which are non-atoms. So if you look at the real line, we have these atoms here. So we have some atoms there. We may have actually lots of atoms somewhere, but it's anyway, it's a countable set. So then these atoms are there. Now pick any points A and B. So we pick A there and B there. So then for these intervals, mu1 and mu2 are equal. Okay. What we want to do is actually prove that also if we pick an atom, if A and B happen to be atoms, so then this is true still, this equality. So think about this. Let's pick now A and B. Let's pick A to be this atom here. So it's atom for either mu1 or mu2, we don't care, but let's pick A to be this point. And let's pick B to be this atom there. So it's also atom of either mu1 or mu2, but we don't care. So what do we do next? We approximate this A by taking some points xn, approaching to the left. So we take points here and they approach this point, this atom, when we go there. We also do the same here. We pick some points which approach B from the other side here, and they approach this point B. And then we want to pick these points, xn and yn, to be non-atoms. So these must be non-atoms. Can we pick these to be non-atoms? Yes, because only countably many points are atoms. So between every two atoms, there's always lots of infinitely many real numbers. So we pick these non-atoms x and y approaching A and B in this way. So then we know that because x and y and are non-atoms, we know from the Lévy's inversion formula that this is true, this equality for all x, for all n in this case. And then when xn approaches A and yn approaches B, so then these intervals are growing. So then we have monotonicity of the measure. So we have growing sets. So then they grow to the interval AB, the open interval. And these grow to the open interval AB as well. So here we have a limit, here we have a limit. The limit must be equal because everything pre-limit is equal. So we know that, yes, this is true for all A less than B, be they atoms or not. So if the Fourier transforms are equal, then the measures must agree on all open intervals of this form. Then what? Then we need to recall the first week of the course. Go back in time 5 weeks behind. Remember that this type of open intervals also constitute a pi system. We have a pi system which generates the Borel-Sigma algebra. So we use Dynkin's identification theorem. And then we are done. This must agree for every Borel set if they agree on a generating pi system. So with the teamwork of Paul Lévy and Eugene Dynkin, we have been able to prove that yes, the Fourier transform fully determines the measure.